I don't want to start my parabola introduction with the most familiar parabola. Because this is the graph of such a simple power function, it's looked at a lot, and we use that as one of our basic functions to start things around, but it's your most straightforward parabola graph. But I want to point out a feature of this that we're going to think about for this section. So for the more details about what's going on with the parabola, there's these points which are kind of nice because the same distance up is over, and that kind of goes with the number that's here. That's kind of a nice thing, but there's a more important point if we zoom in right around here and think more about what's going on there. I want to think about a certain value for which this distance here would be twice as much across here. This is 2p in either direction out here. That ends up happening on the graph of this when the height is 1/4. This point, the height would be 1/4 when x is 1/2. Right, 1/2 squared is 1/4, or negative 1/2 squared is 1/4. So those would be the coordinates of the point up here that have this neat property that the distance from the vertex at 0, 0, the distance there is quarter, the distance in the other dimension is twice as much in either direction to those points. That ends up being a kind of a key point we call the focus on this. And the directrix, if we go the same distance in the other direction, down minus p, sort of we'd have a line down here. And as it turns out, the distance relationship is an interesting one here. That the distance from this point to a point on the parabola is the same as the distance from that point on the parabola to this line down here. That's the distance relationship that connects them, and it makes that one important point right there. We're going to look at the connection between that and the equation here, how to find that p. For this one, x squared equals y. We're used to the y equals form of these things, but I actually want to put them in the form of getting the perfect square by itself. And thinking of this as x squared equals 4 times p times y, we would need 4p to be equal to 1 for this one. So I want to think of it as 4 1/4 y x squared. That value is the distance right here that we want to look for. So if we have some other y equals, we actually want to think of it in x squared equals form. This one's negative, right? So that's going to be a downward parabola. So the p value would be some negative value. I'd come down to the focus on it. I expect some negative value for that. And if you put it in x squared equals form, it's negative 1/3 y. And if negative 1/3 is supposed to be 4 times p, then p would have to be negative 1/12. So I'm going to think of this as x squared equals 4 negative 1/12 y, and that point, the focus point, would be 1/12 of a unit below where the vertex is on this. So far we're keeping these at 0, 0 as the vertex of it. So the focus point there would be at negative or 0 negative 1/12. We're going to look at how that's connected more to the equation some more, but I want you to look first at one other feature of the graph that makes that focus an important point. I wanted you to be aware of one other property of this sort of key point that I was talking about, the focus point to this parabola, why it's actually called the focus, and what it has to do with focusing things is it's a reflective property, really. That's the main point that we were talking about on function y equals x squared. And if I have any line that's coming straight down from above and reflecting off from this, so the angle of incidence and the angle of reflection are the same, that line segment's going to come right down to this one point where everything kind of focuses together here. So for any of these straight line rays, they're going to reflect right to this point. So if you're looking at a satellite and you're taking all of the radio input of some sort from a satellite and reflecting them to a single point, then you can have your receiver here and you can get a really strong signal. So this is a parabolic reflector for a satellite dish, or the other way around, if you think of a reflector shaped like this with a light source right here, like a little filament or bulb right here, that light is going to reflect out and all go more or less in a straight line out of it, so it's good for a directed light, like headlight bulbs would have a parabolic shape to them. That's that same key point that we were talking about in the earlier part of the video. And so if I put in a different A value, I could make this much smaller, and the still going to have a focus point, but it's going to be at a different value now. That's the key point on this one, the focus point. This distance is half of this horizontal distance, but it still has that reflective property that it comes in toward that point right there. So y equals 1/8 x squared would be x squared equals 8y, and the value of that p is going to be 2 there. That would work for various stretches or compression of this. Okay, now for some more variations on this thing, using that same property, but thinking about some other directions too. We could also have the x equals y squared versions of it. Regular x equals y squared is like your square root function, except x equals y squared when y can take on the negative values also, so it's really that sideways parabola. It would look like that. Same graph, just turned sideways. So if this y squared term is there and not the x squared term, then you're going to have a sideways parabola opening to the right or to the left. This one's got the 12 on it, so this is going to be a really thin parabola this way, really stretched out in the horizontal direction. Small values of y either way would give you a great big positive x value. So it's really stretched out like this, which means also means that the focus point is going to be here really close to the vertex. So let's write it in the appropriate form to find the focus here. If we solve for the y squared in it, we get y squared equals 1/12 x. I'm trying to think of y squared equals 4p times x. So p has to be like 1/48. You're solving out where this is equal to that, and you get this really small value. Y squared is 4 times 1/48 x. So the focus for this red one would be 1/48 to the right from the vertex. Be right up in there. Okay, so starting from the equation, it's kind of that form that we're looking for, although we might have an h and a k. We might have a shift horizontally or vertically, so we might have x minus h and y minus k going on. I got a couple examples for that where you have to rearrange the equation a little more. To sort of get y squared by itself in this thing, I gotta move the 16. So I'm gonna have x minus 16 equals 12y squared. So y squared is 1/12 x minus 16. Now I want this to be the 4p out here. I want y squared equals 4p x minus h. Now it's going to have a horizontal shift to it, and the h is 16. It's all just matching up what numbers work here. P would have to be 1/48 again, positive 1/48 for this one. So that comes out 1/12. So h is 16, k is still 0. So the vertex is at 16, 0 for this. And the p-value is 1/48, so the focus is just 1/48 further to the right, positive, in the sideways direction here. It's a y squared thing, so it's a sideways parabola. Just as steep as the one we just looked at, but moved over there. So when y is 0, x is 16, that's clearly a point on it. But otherwise, x is going to be much bigger than 16 as I get further out, so it only goes to that side. Okay, so rearranging this into the form perfect square equals 4 times a number times whatever that. This one's got an x squared and an x term, so in order to get perfect square on one side, it's going to have to be this kind of perfect square. In other words, we have to do completing the square on these things to make that perfect square show up. So this divided by 2 is 3. 3 squared is 9. I'm going to have to add 9 to both sides. So I can rewrite this as y plus 9 equals perfect square. Now I got this by itself. It's supposed to be 4p y minus k that's over here, but it's x plus 3 squared equals y plus 9. So I guess k is negative 9, and I don't have any number outside of there, so it's 1. The 4p has to equal 1, so p is 1/4. I have perfects, and h equals negative 3 here. So I have this form. When h is negative 3, that's x plus 3 squared. So I'm making this match up. 4 times 1/4 is 1, and y minus negative 9 is y plus 9. So that's exactly what our equation is. We got to make those values match up, and that tells me what I need to know about the graph. First of all, this is an x squared thing, so it's a vertical parabola, opening up or down. P ended up positive, so the focus is up, it's opening up. It's a regular x squared kind of direction to it. The vertex is at negative 3, negative 9. And it's going up from there with a p-value of 1/4, just like your regular y equals x squared thing. It's that kind of shape. You could find more points on it if you want to plug some values in and plug points, but the vertex is there. And the focus is just up 1/4 from that, because we have p equals positive 1/4. So negative 3, negative 9 plus 1/4 would be negative 8.75. Would be the focus point on that. Would be 2 times p, or 1/2 a unit over in either direction if you wanted those values. So that's the vertex and focus for that one. That's some of the work that it takes to get the equation written into the right form to read that stuff out. All right.